In this video I'm very quickly going to talk about electromagnetic radiation and how it's produced in this funny thing called polarisation. Most important thing about electromagnetic radiation is, if the beam is travelling this way and the E field is in this direction, well then the B field must be in this direction. We say that the direction of the electromagnetic radiation is orthogonal or perpendicular to both the oscillating magnetic field and the oscillating E field. It's customary when you're talking about which is oscillating, the E field or the B field. Normally you just talk about the E field even though you know there's a B field going perpendicular to it. Okay, the first thing is how is electromagnetic radiation created? And electromagnetic radiation is created when you've got an oscillating charge, typically an electron. If the electron is oscillating in an up and down fashion, that means the E field is oscillating in an up and down fashion. If the electron, say, is emitted in this direction, if it's going up and down in this direction, the B field, the magnetic field, must be going in this direction. Now, so how is electromagnetic radiation produced? Well, when things are hot, they contain lots of jiggling charges, if you like. The charges will jiggle with various frequencies, but there will be a median frequency with which they jiggle. Now, as you increase the temperature of something, you increase the frequency with which they jiggle, and if you increase it hot enough, you will get to a point whereby things are jiggling at about 10 to the 14 Hertz. They'll begin to become visible. That happens for red light at about 1000 degrees Kelvin. And if you want to see all colours, I'd say at about 3000 Kelvin, you will have a body which is jiggling. There'll be enough charged particles jiggling with enough frequencies to produce all the different frequencies of light. Now, the thing about hot bodies is when the charges inside them jiggle about, using loose enough language, well, what happens is some charges jiggle in that direction, up and down, and so they will produce an E field which is going up and down. Other charges will be jiggling side to side, so their E field will be jiggling side to side, their B field, consequently that side if it's moving that way. Some will be going like this. What is produced is known as unpolarised light. That means light in which the E field is in every possible orientation. Now, if I want to produce light in which the E field is only going in one direction, say for instance this direction, well, I can then, my choices are, I either produce it by only jiggling charges up and down in the same direction. That will give me polarised light. Another way I can do it is by using things called polaroids. So, this is a polaroid. Now, this polaroid will only let light through in this direction. The first thing to notice about a polaroid is when you look at light coming from a polaroid, so this is coming from my face to you, there's a decrease in intensity. Indeed, the intensity is decreased by half. And that's because essentially you've cut out all the light where the E field was going like this. You're only letting through light in which the E field is like that. If I put a second polaroid in the exact same orientation to the first, the decreased intensity isn't too much more. What you need to be aware of is what happens as you turn two polaroids relative to each other. As you turn them, what happens is the amount of light transmitted gets less and less and less and less and less until when they're turned through 90 degrees, no light is transmitted. And then as you turn them through a greater angle, it increases until it's back to a maximum when it's turned through 180 degrees. If you turn them again, you get the same phenomenon. Now, I suppose the first thing to notice about polaroids is they're actually not 100% efficient. And you can see this with a laser. If I get my laser and I shine it at the board, you can see, this is a very strong laser, that as I turn the polaroid, you get a decrease in frequency, increase in frequency, depends what it's scattering of, decrease in frequency, increase in frequency. So the first thing, and if I pass laser light through cross polaroids, so they're not crossed, if I cross them like this, so you'd think no light can go through that, but the laser light can. So polaroids aren't perfect, they won't cut out 100% of the light. Polarisation can occur due to two other processes, which I've talked about in other videos. It can occur due to reflection, and it can occur due to the scattering of light off small particles. If you want to see more information on that, watch the other videos. Not massively important, apart from the fact that you know that it happens. The other property of light I want to talk to you in this video is about, it's got to do with optical activity of materials. So, some materials are said to be optically active. So what that means is, say for instance, you're seeing this, this piece of plastic is optically active. Now, if I put a polarizer there, well, that means what you're seeing is the light that's coming from behind this and through to you in the camera. What's happened is you're looking at polarized light. Now, this material does something funny to polarized light. What it does is, say for instance, when the light comes through to it, the light is polarized in this direction. The E field is only vibrating in this direction. As it travels through the material, the E field gets rotated. So that when it's finished travelling through, the E field may be orientated, what's that, 30 degrees, 45 degrees. It can be turned through that angle by passing through this material. The upshot of this is that if you pass light through two cross polarizers and material which is optically active, you will still be able to see it. So here we are. I've got two cross polarizers, and you can see that they're Polaroids because you can see through this, but now you basically can't see through that. And if I put this in the middle, oh, there it is. If I put this in the middle, I should be able to see that. Now, you can sort of see it, but I'm going to use a stronger light source. So, let's have a look. And there you go, you can quite clearly see, in the middle of this, you can see that piece of material. Now, the other thing, a related thing to optical activity is, let's see if I can see it, that changing of colour. So as I flex, I'm just trying to see where the best place for this camera is. Do you see that change of colour? That change of colour is known as photoelasticity. And photoelasticity is a technique for understanding, or for visualising the stress concentration of materials. Where the material is changing colour most rapidly, that's where the largest stresses are. In other words, that is where that material is likely to break. The reason photoelasticity works is because when you stress the material, effectively what you're doing is you are changing the optical activity. And where you change the optical activity fastest, that is where the stress concentrations are building up. So, photoelasticity is a technique for viewing the stresses in materials, particularly irregularly shaped materials, where it might not be simple to figure out where the stresses are naturally occurring.